Hey folks, Mr. Dell here. Hey, we're looking at a problem where we have some functions. They're all exponential functions, so we're gonna explore those, complete a table and graph, and talk through some of those characteristics. This is a problem coming from CPM's Integrated Math 1, and this is section 8.1.2. So number 8-26. It says the functions f of x is equal to 2 to the x. So you have this function. So there's three different functions. You have that function, and then f of x is equal to 2 times 2 to the x, and then f of x is equal to 1/2 times 2 to the x. All have the same multiplier, right? So what do we know? Well, reminder here. So when you have something in the form of f of x is equal to a times b to the x, right? So your a value is your initial value, right? It is your value at x equals 0, right? It's the y-intercept, your initial value at x equals 0. That's your 0 term. Your b is your multiplier. That's your common multiplier, or maybe even call it the common ratio if you look at a sequence, right? When we were dealing with geometric sequences, that would have been the common ratio, right? So there's ways to find that. So each of these, then let's start off with the first one. The first one we're going to do is 2 to the x. So my f of x is 2 to the x. So if I'm going to complete this chart, first of all, I like to start here really, because I know what my 0 term is, my a. Well, what is the a? What would be that initial value? Well, when there's nothing written there, there's always this 1 times it, so it's really 1. The other way that you can look at it is if I take 2 to the 0, well, 2 to the 0, anything to the 0 power is 1. Okay. So then from that point, remember your common multiplier is 2. So that means going from one next to the next, it's just multiply by 2. You're going to multiply, you're doubling it every time. So 2 times 1 is 2, 2 times 2 is 4, 2 times 4 is 8, 2 times 8 is 16, 2 times 16 is 32, right? So this is that way of completing that table because you're just dealing with a common multiplier, right? You could also, every one of these, you could put in, say for this, you can put the x as 4, and we could say it's we need to figure out what is for this one 2 to the fourth. Well, that means 2 times 2 times 2, so it's 16, right? So if you're multiplying by 2 to get to the once you have a value, also to go backwards, you would divide by 2. It's opposite in this case. So I divide by 2, I get 1/2. Divide by 2 again, I get 1/4. Divide by 2 again, I get 1/8. Okay, so there's my first table. My second table, I'm going to do for this function, which is 2 times 2 to the x. So once again, my 0 term, right, is the a value. It's where the x equals 0 is that a value. So what's my a value in this case? My a value is 2. So I'm going to actually start with 2. And then I'm going to multiply each term, right, to get to the next term. So so we're going to go 2 times 2 to make that a 4, times 2 again to make that an 8, times 2 again to make that a 16, then 32, then 64. Right? Does that make sense? So again, we'll go reverse, divide to get these terms. So 2 divided by 2 is 1, divided by 2 is 1/2, divided by 2 is 1/4. You can see a similarity here really with the net answers that we're getting each of these. So we're going to talk through that too. So here's the last one, 1/2. So the function is 1/2 times 2 to the x. So my 0, right, my initial value, my 0 term is 1/2. So I'm going to put a 1/2 in where x equals 0. And then again, it's your common multiplier is 2. And I forgot to answer that question. What is the common multiplier? The answer up here is 2, right? So I'm multiplying by 2 every time. 2 times 1/2 is 1, times 2, times 2, times 2, times 2, right? Doubling. And then the last, going backwards, is dividing by 2. If your common multipliers going forwards is that going, so that's going to be 1/4, 1 eighth, and then 1/16 when you divide by 2 every time. Because remember, dividing by 2, by the way, is the same thing as multiplying by 1/2, if that helps you to see it. So I'm actually multiplying by 1/2 every time I go backwards. That's the same thing as dividing by 2, multiplying by 1/2. All right, so I got my table filled in. So it says, how can you use these tables to determine the multipliers? Well, it, how we actually completed the table. We completed the table using the multipliers, right? To find your multiplier, to find your b value. Your b value is that common ratio, right? So what we do is we divide the one term. So we'll say a to the n plus 1 divided by the term prior to it, right? That's how you find it. If you're going by ones in this case, and we are going by ones on my x, so it's dividing, right? So we're going to say the 16 divided by 8, which is 2. That's my common multiplier. So that's how we use the the tables to determine the multipliers. All right, is so we could say divide. Actually, I'm going to just utilize this divide the one term by the previous term. You could say a to the n plus 1 divided by a to the n. Okay. All right. Last thing, part of this, it says on the same set of axes, sketch 3 functions to describe the similarities and differences among the graphs. So if I graph, let's graph this one first. So I'm going to graph y is equal to 2x. So remember, f of x is the same thing as y. That's my y-axis, or you could call it my f of x axis, and that's my x-axis. So let's start with the f of x is equal to 2 to the x. Well, I can look at my points and use my points to graph, right? And I'm going to just start with my 0. I always start with my 0. That's my y-intercept. So my y-intercept is 0, 1. So I know it crosses right there. And then at 1, what did we get? At 1, it was 2. At 2, it was 4. It doubled, right? So at 1, it's 2. At 2, it's 4. At 3, it's 8. At 4, it's doubling, so I'm at 16. At 5, I'm at 32. Right there. I think that's as far as I can go, because at 6 would be 64, which off the graph. And then we notice going backwards in the negatives, right? What do we see? In the negatives, the numbers were just getting smaller. Negative 1 was at 1/2, and then 1/4, and then 1/8. So it's cruising down and getting closer and closer to 0. So what my graph looks like is it looks like this. Okay. So that's f of x equal to 2 to the x. My f of x is equal to 2 times 2 to the x. The only difference here with these is it's the same multiplier, but I have a different initial value, right? This 2, remember, is my initial value. So if I'm graphing that, I'm actually starting at a y-intercept of 2. And then everything is shifted from there, right? So at 1, now I'm at 4. At 2, I'm at 8 because it's doubling. At 3, I'm at 16. At 4, I'm at 32. So if you look at and then again, going backwards in the negatives, it still decreases. At negative 1, it was at 1. It still has the same end behavior. As x gets more negative, as x decreases and gets negative, it's approaching 0. So it's the same end behavior, and we're going to see that for all 3 of them, and I'll write that down in just a moment. So the last one we'll make here in red, 1/2 times 2 to the x. Again, the only difference really it's going to be is that this time it's going to start at 1/2. So at the x value, right, where x is 0, y is 1/2. And then everything else is very similar. At 1, it goes up to 1 because it doubles. At 2 is at 2. At 3, it's at 4. At 4, it's at 8. So every time it's doubling now. And 4 was 8, so 5 is 16. It's doubling. And 6 is at 32. So once again, the end behavior is the same this direction. It gets closer and closer to that 0, but never crosses that x-axis. And it goes up. So those are the 3 teams. So one of the things that is the similar, because it asks the similarities. One similarity is same end behavior. Okay, which means what? As x, we can say it this way, gets more negative, then y approaches, and we're going to use this arrow, approaches 0. It's never going to equal 0. It's going to approach 0. right? It gets closer and closer to that zero, but never crosses it. So there's an asymptote. What we call is so we would say, therefore, it's called a horizontal asymptote at y equals 0. So we have this horizontal asymptote. It never crosses it, but it gets closer. That's what we call horizontal asymptote at y equals 0. Okay. We'd also look and to see that it's got the same steepness, right? Because as it just shifted over in a sense, same steepness. Okay. All right. So I think that's good enough for right now. So there we have it. So you've got your graph, your tables, and your descriptions. All right. Hope that helps.